Student wishes to determine the power dissipated in a variable resistor connected to a cell. Part of the circuit for this experiment is shown in figure 3.1. Complete the circuit of figure 3.1, showing how the variable resistor is connected and how the potential difference across it is measured. Right, again, they're not asking for much here. So we've got to put the variable resistor in. So the resistor with the arrow through it, we're going to want to measure the voltage across that. So we just put our voltmeter in parallel. Right, okay. Figure 3.2 shows the variation of PD across the variable resistor with current. Okay, so they're just taking their ammeter and voltmeter readings, plotting those out. Potential difference V across the variable resistor is also the terminal PD across the cell. Yes, describe how the potential difference across the cell varies with the resistance R of the variable resistor. Suggest why the terminal PD varies in this way. Right, there's a number of ways you could go about doing this. We could do one of these chains. We could say that the EMF is divided between the internal resistance and the variable resistance in proportion to the resistance. Proportion to resistances. Therefore, as R increases, so the resistance of the variable resistor increases, then the terminal PD must increase because we're getting more of the EMF is then being allocated to the variable resistor. So that means our terminal PD is going to go up. And then we could say also that as R goes down, the terminal PD goes down. So that's one way of putting it. We could go, and this might be a safer way of doing it because it's quite often safer going to the equation. If we do the internal resistance equation, so our EMF is equal to the voltage across the internal resistance plus our terminal PD, internal resistance, plus our terminal PD. So this is just doing our Kirchhoff's second law and saying, right, well, our PDs are our PD across the whole circuit plus the PD across the internal resistance. So that's our Kirchhoff's second law. And we've got that, well, E is fixed and so is little r. They're both fixed. So we can say, therefore, as R goes up, I will go down because that's what happens. If you increase the resistance, the current will drop. So V must go up according to that equation. So that might be a safer way of doing it. You increase the resistance in the circuit, the current drops. If the current drops, then according to this equation for fixed E and R and a drop in I, then V must go up. So our terminal PD must increase with resistance. So two different ways of answering that one. And it's filled up pretty much all the space I've got on this, which is annoying. By referring to the points A and C, justify that the power dissipated in the variable resistor is a maximum at or near point B. Right, this is a weird... Yeah, slight, I suppose it leaves you hanging a little bit as to what they're saying. Well, how are we meant to be referring to these 2 points here? The way I'm going to go on this one, I think, is to get an equation of this line. So let's do a... This is almost certainly not going to be what they have in the mark scheme, but still, I think this is a good way to go about it. So let's do... I'm going to squeeze things over here because I don't think this will take much space. So let's do a y equals mx plus c on this, which means that we've got the... let's drop down a bit. So v, which is our y, is going to be our dy, so our change in y is, and this is negative, so minus 1.4 divided by, what's this going up to? Oh, that should be a 1 there, that's dropped off, so that's 1.5, 1.6. So that's the gradient of the line, minus 7 over 8, multiplied by I, and our c is 1.4. So we've got an equation for the line there, and then we can say, well, our power is V times I, which is going to be minus 7 over 8I squared plus, what have we got there, 7 over 5I. So we've now got an equation for P just in terms of I. This is turning this straight line into a parabola. So let's then factorize this, I suppose, which means we're going to get, God, I really don't have space for doing this. So P equals, we've got a 7I we can take outside, and then we're going to have 7I, so we've got I over 5 minus, oh no, just 1 over 5, sorry. 1 over 5 minus I over 8. So if we're going to then get we want a maximum of this, we're wanting to get the maximum power. If I'm doing this without referring to points A and C, I don't know why A and C are particularly useful in this. Anyway, I'll come back to that once I finish the sensible way of doing it. So we know that the maximum on this, we've got a negative quadratic because we've got a minus I squared, so we've got something like that. So the maximum is halfway between the roots. So it's going to be halfway between 0 and whatever the root of this is going to be, which is 8 over 5. So our maximum is going to be half of 8 over 5, which is 4 over 5. So P max when I equals 4/5, which is pretty much where B is. So at B. Right, so I've done that without any reference to A and C. I suppose maybe what they're getting at, because I mean, this isn't complicated. I mean, this maths we've done here is GCSE maths. Admittedly, we could have at this point here, I mean, you could differentiate, you could do some calculus. They can't assume anyone knows how to do calculus because you might not be doing A-level maths. And also you don't need, as we just shown down here, to know calculus in order to find the turning point of a parabola. So maybe by referring to these points A and C, they want you to work out the power at A and the power at C and say that B is going to be somewhere in the middle. But that's just a stupid question. I don't see that it's going to be any better than this. I mean, this is the way to go about it as far as I'm concerned. So I don't really know what they want in terms of referring to A and C. Actually, I'll do a cop-out on it. I'm sure this isn't what they want, but they're not making it particularly clear, and I've given a better answer than they were probably expecting. So I'm going to use A and C in order to work out the gradient of the line. And we'll just go off of that. So I'll replace that minus 1.4 over 1.6 with a triangle that goes between A and C. And then it does what they want in their stupid question. And it still comes up with a much better solution than they probably thought of. So let's leave it at that. Not very impressed. Determine the EMF E of the cell. Right, the EMF, well, that's just going to be our 1.4 volts. Yeah, when we've got no current flowing through the circuit, then if we do our E equals I times internal resistance plus V, then that bit just disappears. And then we've got that our EMF is equal to terminal PD, which is 1.4 volts. Calculate the internal resistance R of the cell. Right, well, we can use this equation again, but we take 0V. So we say that EMF 1.4 is equal to I times R. So what have we got here for I? 1.6 times little r. So that's when V is equal to 0. We've got a current there of 1.6. So that means our internal resistance is going to be 7 over 8 ohms. So about sort of 0.88. Right, that's done all of those bits. Last parts here for part B. In figure 3.1, which one was that? Oh yeah, that's the circuit. The cell is replaced by a solar cell as the source of the EMF. Solar cell transforms light energy into electrical energy at maximum intensity of sun on the solar cell is 800 watts per meter squared. Surface area of the cell is that. Define the term intensity. Right, so intensity is, well, it's power per unit area. Oh, I've missed out per. So power per unit area. the maximum power delivered by the solar cell to the variable resistor is 0.25 watts. Determine the maximum efficiency of the solar cell. Okay, right, so they've given us the wattage here that is produced. So we need to get the wattage that's actually landing on the solar cell. So we've got 800 multiplied by 2.5 times 10 to the minus 3. So that would be a quarter times 10 to the minus 2, just making it a bit easier to mess around with. So that'll get rid of those, which means we're going to get 2 watts. That's what's coming in. And we've got 0.25 going out. So we've got a quarter divided by 2 gives us a half. So our efficiency maximum is equal to 1 over 8. So 12.5%. Right, that's actually quite a nice question. You've got the weird bit about the second bit here, but all in all, it's yeah, I quite like that one, I think. Well, I've got one more question to do anyway. Figure 4.1 shows how the resistance of a light-dependent resistor varies with the intensity of light. State how the resistance of the LDR changes with light intensity. So resistance decreases as light intensity increases. I mean, we might want to put in something as well that the largest change in resistance is greater at lower light intensity. So we're just saying a couple of things. We're saying something about the shape of the graph there as well as just the fact that the resistance is dropping as the light intensity increases. Figure 4.2 shows a light sensing potential divider circuit, LDR, connected in parallel to a voltmeter and a data logger. Right, okay. Battery EMF 9 volts, that's in the picture, 1.2 kiloohms in the picture. Potential difference across the LDR is 6 volts. State the potential difference across the 1.2 kiloohm resistor. Right, well, it's got to be 3 volts so that the 3 and the 6 can add up to 9. Kirchhoff's second law. Calculate the resistance R of the light-dependent resistor. Right, well, if it's got double the PD, it must have double the resistance. So it's going to have to be 2.4 kiloohms. Use figure 4.1 to determine the light intensity when the PD across the LDR is 6 volts. Right, so what were they showing us on the previous picture again? So that is resistance against light intensity. So for 2.4 kiloohms, what have we got? We got 2.4, that's here, which is about here, which looks like 50 watts per meter squared. So 50 watts per meter squared. Figure 4.1 shows that the change in resistance when the light intensity rises from 60 to 80 watts per meter squared is 0.5 kiloohms. State the change in resistance when the light intensity rises from 20 to 40. Right, so from 20 to 40, we're going from 5 down to, what's that, 2.8. So we got a 2.2 kiloohm resistance change. Okay, this is all so far so good. Larger changes in data logger voltage are observed for changes at low light intensity rather than at higher light intensity. Explain this. So, well, we've got that the voltage is proportional to the resistance. So a large change in resistance at low light intensity will lead to a large change in the potential difference. So that's following on to our description of the graph that we did in part A. When the circuit of figure 4.2 is operated for a long time, the carbon resistor becomes hot. The resistivity of carbon falls as the temperature rises. Okay, state and explain the effect on the potential difference across the LDR. Right, so let's move it up here then. So as our resistivity drops, that means our resistance is going to drop, which means our potential difference is going to drop. So the potential difference across the LDR will increase because all of this is for the fixed resistor. This is for the fixed resistor. So if you were going to write this out then in some kind of sentence, because maybe this is even more shorthand than I'd normally do, you can say, well, for the fixed resistor, as resistivity drops, resistance drops, so PD drops, and then you can do, therefore, PD across the LDR increases. Right, that's that one. Last bit. Describe briefly 2 advantages of using a data logger to monitor the variation of light intensity falling on the LDR. Right, well, it does continuous recording over time. That's a good one. It's automatic. You don't have to do everything by hand. It's doing automatic recording of data. You can feed your data straight into a computer for analysis. So, that's 3 things. Pick 2 of those. Right, that was actually quite a quick question considering what it looked like to start off with. But yeah, that's those 3 anyway. I'll leave it there for now.